certified with Data Vault. I have a book out, The Enrichment Game. If you want to chat about data, about anything related to data, I'm happy to talk about it, whether that be one-on-one or podcasts or what have you. Uh, so that's me. All right, I borrowed this slide from one of our sales presentations, so I need to let it play out. All right, there are a lot of people that are on this call that could take a lot of open source tools, combine them to make things work for your enterprise. You guys are awesome. But are you focused on the right problem? Are you running things quickly and efficiently, or are you going the wrong direction? One of the things that I'm a big fan of, and I'm sure Neil and some of the other folks in the Data Vault community are, is automation. So one of the things that you really want to try to do as much as possible is focus on automation of the things that can help you, so you can focus on more of the business value add stuff. All right, so I have to go through a few definitions here, and then we're going to combine all these things, and we're going to talk about what this means from a Data Vault perspective. So one of the things when you start from first principles is what are the first principles that you're starting from. So these points come from Euclid. These are the first 7 definitions from Euclid in his book, and they're illustrated in the first three images. So just based off of our first 4 images, so just based off of some of these basic definitions, ultimately we can create something with a volume here on the far right, uh, just by following some of these definitions. So first principles are very important, understanding how to put things together. So um, one of the things I talk about from an axiomatic perspective is with axioms are definitions that are assumed to be true. They're very simplistic definitions, but you can build on them. And so it becomes very important when we do talk about first principles and an axiomatic approach to anything, that we have very clear definitions of things. Uh, all right, so what are the various things that we work with on a daily basis? When it comes to building things like Data Vault, we work with business keys, relationships, context, and measures. Well, in mathematical terms, these are can be interpreted as sets, tuples, and traits. And these are the easy parts. So how do we get from our data infrastructure to the business world, rather than focusing on the low-level details, infrastructure details? There's a way to translate that in business speak, and some of that you have to do with a little bit of math in order to get to where things are translated easily between the business and the technical side.
Live
So
updates.
say again, was that a question?
I think someone had their mic open.
Okay. So quick little definition here, set. Hopefully everyone's familiar with this. This is set builder notation. If anybody has any questions about that, we can, please reach out. I'm happy to share. But what this says in words is that this says that the set X exists such that X is in domain D. Now the beginning of relational theory, what we all work with relational databases, was entirely built off of set theory. And in the original papers, the concept of a relation that Codd and Date put together was built off of the definition of a set. So a relation is a collection of elements where the element is a name paired with a domain or data type, and all elements have a unique name. That's the definition of a relation according to the original stuff. A Relvar, on the other hand, is an implementation of that. So you can think of a relation as the table structure, and a Relvar as a row. So it's an implementation of the row. Now, um, a tuple, as I mentioned it earlier, an n-tuple is a finite sequence of elements. So a row can also be considered to be an n-tuple based off of the way that it's put together. And because of that, and the fact that there are a few different interpretations about how you can apply tuples to various problems, whether that be a function or another relation or whatnot, we'll talk about that more in a later in a later part. So some of the definitions in Dates writings, given a relation, the heading of R denotes a certain predicate, where a predicate is just a truth valued function that, like all functions, takes a set of parameters. And this last quote is from the part suppliers example that Chris Date writes a lot about. Now, a relational data model, I kind of had to put this together just because I could not find anywhere a good mathematical representation of what a relational data model is. And I needed that for some other research that I was doing. So I just put one together. It's very simple. A data model is defined as a set of relations in each alpha. So an alpha is a superset of a domain, a business domain. So whether that be orders, accounts, any of those kinds of things, all of the relations that are in that domain for a given application and their relationships and such is a relational data model. A set of foreign keys. These are the keys that are defined that relate each of the relations together. So that you can tie, this is what you're going to be doing joins on, this is how you're going to be making the more sophisticated queries. Entity relationship diagram. This is a graphical illustration of those things. So each of the relations, each of the tables are here, and then the foreign key relationships are the lines. So with just dots and lines, we can represent a lot of very interesting things. Now, data modeling has never really been under attack more than it is today. There are people who advocate a message of you don't need to design anything, just throw it together and put it out there. And everyone's interchangeable. Our business users are the only ones that should tell us what we need to be working on. Well, I don't that message I don't completely agree with. The application development approach is not necessarily the only way to do anything. So one of the things that I'm recommending with some of the math that I'm talking about here is you can take these artifacts that a lot of application development teams may discard, and you can do some really interesting things with it from the perspective of applying a little bit of math to it. So we'll get more into that. All right, so here's the beginning of some of this stuff. So a data structure graph, what I just showed, that entity relationship diagram, the ERD, before, you can think of that as an actual graph, where a graph is defined here, an unordered set of pairs, pair sets where the elements of V are vertices. So the vertices in this is a table, and the set of pairs, E is the set of pairs called edges of elements of V. So what this means is the lines here are foreign keys, the dots are the tables. Now, by following this with a little bit of rigor and a few other things, this is actually a proof, or could be considered a proof, that an entity relationship diagram is a graph by definition. Now, when it comes to, again, looking at this from a mathematical perspective, a topology is slightly different from a graph in that there are defined lengths of the edges. A graph does not necessarily have a length associated with the edge, but a topology does have a length associated with an edge. Now, as we're moving data around from one system to another, where if you think of an application data model that is sitting within some server somewhere, that data model is actually a graph. When you have to move data out of that data model into another location like a staging area and prepare it for data vault transformations, that now becomes, there's a length associated with it. You're doing a movement of at least one step that's one unit away from the application to the next layer, which is going to, your staging layer, and then the following layers from there, your raw vault, and then on and on. Each of those steps, there's a length associated with it. Now, um, why do we care about this? Well, there's different kinds of math that can be done between with a topology versus a graph. In Vermont, and I cannot do this on this forum just because we're all virtual, but in Vermont, one of the things that I did is we took some yarn and actually threw it into the audience. I think it kind of surprised a few people, but you kind of toss it around. And so we had these three groups of three sets of chairs where people were there, and they would toss the yarn about just a little bit. And then I was holding on to a section of the yarn, and then I gave the other end of the yarn to my assistant Sam, who works for Neil. So the illustration there, of course, is each of the application data models are going to be slightly different, but bringing that into an enrichment platform, a staging area, there is at least a length of one. So there's some kind of transformation logic that is happening, or movement logic that is happening to pull the data from the application into a staging area. And then there's a whole nother process where you have to do something from the staging area to your proper enrichment platform, whether that be transformation, whether that be creating data vault model, populating a data vault model, populating a dimensional model, what have you. So you can think of an ETL architecture in a lot of ways as a data structure topology, whereas a data model is more of a data structure graph. Application data model, just as I mentioned, it's purpose driven for the performance of an individual application. An enrichment data model is much more generic. It has a lot more things going into it. The sources from an enrichment data model are going to be coming from both within the organization, external to the organization, third-party data feeds, enrichment data, weather data, what have you. So this is just a very generic picture of what an enrichment data model is going to look like. A dimensional data model, we all love these because they're great from a performance perspective when it comes to representing data. There's really only two types of tables there, the dimensions and the fact, and we'll revisit that in a moment. Now, Data Vault, hopefully all of you are familiar with Data Vault here, but I'll give a quick little overview of that from this perspective. So the most important topics is the business key. The business key, or the natural key, is the key that the business uses. So that's going to be going into the hubs, which those are the circles that we have here. And then we have links, which shows the relationship between, in this example, customer, product, and order, and then satellites, which do a description of either the hub or the link. Some overall definitions of metadata. There's a lot of metadata that goes on in our world with working with enrichment platforms. I'm not going to read all this to you, but it'll be in the, I'll make sure this is in the PDF that Neil makes available. Now, putting all this stuff together, this is where things start to get fun. Now, let me revisit the whole idea of a data structure graph. In the unlikely event that you inherit an application that you need to do some analysis with, and you need to bring that data into your enrichment platform, into your data vault. Just in case you don't have a data dictionary and the tables are not well defined, you may have to reverse engineer that. I know nobody has ever had to worry about doing this, but there are times where you get an application data model and the application developers did not keep a data dictionary. They did not keep good notes about how things are to be used. So one of the things that is useful is to reverse engineer this, but to take it and put it in not just an ERD, but also in a graph. And then from the perspective of a graph, you're able to actually see some very strong relationships here. So in this, the little pink thing in the middle there, that is the central node. If we were to think of that as a table that is to be queried in a relational data model, chances are that table is going to be queried more than anybody else. So there's a good chance that that is going to be one of the tables that contains something important that you're going to need to transform into your data vault structures. And also, one of the things that is useful, because when you translate something as abstract as a data model into a graph, um, just visually, humans have evolved over millions of years to be able to really pick things out of something abstract into something concrete using your eyes. So, quick little eye test here. Can anybody see the frog? I'll give it a couple seconds and let me add a little bit of stuff to it. So, how about this image now that we've got grid lines on it? Is it easier to find the frog? Could be. But also one of the things that you can do with the grid lines is if you can find the frog but somebody else can't, you can make reference to the actual grid squares where the frog is located. And then finally, I've got even more detailed grid. This image is very much language agnostic. If you can see my mouse, that's where the frog is. It's grid T65 to U66. Hopefully everyone can see that. That's where the little dude is sitting there. So by interpreting a data model as a graph, it kind of naturally flows that we're able to interpret things easier. We're able to understand it a little bit more intuitively than reading through all the definitions of things. We know which tables are going to be central, which tables are going to be important. And also we can say there's a good chance that the tables that are located close to the one that is most central is where your business keys are. So again, if you're trying to start from scratch for an application data model that doesn't have a lot of documentation to it, you can do this analysis and you're going to narrow down certain areas where you need to look for business keys in the application. And I claim that any table that is 1 sigma away from the mean degree distribution should have the business keys for this application. So any table that is connected to this, and there may be a degree depth of 1 or 2 here, but all of the tables that are going to be close to this particular table, that's going to be where your business keys are. Stuff that is way out here that only has 1 or 2 edges to it, it may or may not have the business keys, but this is a stronger case. There's a stronger case to be made that the business keys are located centrally. Now, some of the things that we do, and I'm going to read, this is kind of another way of saying some of the other things that I was talking about earlier. From an application, from the applications that are supported, we have to pull data from those applications and then transform it to make it useful for other people, whether that be executives, business analysts, accountants, fiduciaries, what have you. Each of the applications on the left here, these are all designed and customized to be performant for their bespoke purposes. On the right here, we've got to take data, aggregate it, pull it together, combine it, enrich it, etc., and make it useful for the people on the right to be able to answer different questions. Often the questions that are to be asked on the right are not the questions that are asked on the left when the applications are being designed. I've seen that repeatedly. Application developers don't care about the questions that these guys are asking. They don't want to optimize their data structures to answer the questions on the right just because it's going to have a negative impact on performance for their users that are on the left. So building an enrichment platform, hopefully this is obvious to this community, but it's not obvious to everyone. We have a different set of customers completely than any of the application development teams. Now, finding business keys. I talked about identifying where the tables are that may have business keys. How would we use that information? Well, one of the things that I've worked on a few times is trying to find this, and I came up with this approach. So in this expression here, in words, what this expression means is for any column in with several rows R for a given period of time T, both of these are the same time period, what is the unique rate of change of the individual column divided by the rate of change of the unique rows in this relation? So you're taking the distinct rows, the distinct values in the column, and dividing it by the distinct values of the rows. And this is where you do some interesting things like MD5 concatenations and such in order to get the proper things. Repeatedly, whenever I've applied this to any new data system that I've worked with, the columns that this approach identifies are business keys, primary keys, or foreign keys. They're always a key of some type. And this is, so far, knock on wood, this approach has never let me down. And so here's the approach that I take. There's one of the things that you can do with this is you can certainly, it may not be 100% accurate. It may not always tell you every business key within the application, but it will certainly eliminate columns that are not business keys. That I have no doubt. So if you're looking at an application data model that you've never seen before, interpret it as a graph, you do a little bit of this entropy analysis, you could go, okay, I've identified these 15 columns that I think to be really important. You go back to your business sponsor that needs to have some of this information and you say, okay, these columns we think are important to your needs in the future. Which one of them are particularly important to you? This is a very effective conversation rather than saying, I've got 1,000 columns that are defined in this database, and there's no data dictionary, there's no documentation about it. Which one's important? Your business users are going to go, I don't know. I don't, they may know. Some of it, certainly your data stewards, you would hope that they would know that, but then you're going from, historical legacy domain knowledge within somebody's head to this is actually legitimately, this is what's represented within the data itself. This is what the data says about itself. And then there's also some other opportunities for tying this to ontology. Bruce McCartney's done a lot of interesting work with ontologies and such. And I don't know if he's spoken to this group or not, but Bruce has got some really interesting ideas for ontologies. So let's see here. Get to the next things. All right. So once you've got these candidate keys, finding links is relatively easy because you just identify tables in your application system that have two of the business keys together. That's a link by definition. That's really easy. Now, as I spoke about before, why aren't we transforming data? Well, we've got to transform the data because the application data structures are not necessarily optimized to answer the questions of the business users. Is there a way to, is there a mathematical process that can be applied to data transformations? And it turns out there is. As I was studying, reading various books and stuff, there's this mathematical subject called category theory. Category theory has this capability called a functor, a forgetful functor. And what the forgetful functor does is it translates one structure into another. So if you just have a set or a couple of sets, you can use a functor mathematically to transform that into a graph. Likewise, you can use a functor to transform a graph into sets, on and on. So going back to what I originally described, what is the with some of these definitions, our relations are, and I don't know that I've actually said this before, but from a mathematical perspective, a relation can be thought of as a non-abelian subgroup. So looking at this from the concept of category theory and group theory, you have these R subgroups. Using forgetful functor, we're going to transform the business key from that subgroup into a set, which is going to be our hub. That this is part of the set notation. And then we have the links, which are going to be transformed. Essentially, they're going to be transformed as subgroup to subgroup to a link table. And then, of course, the satellites are really just the traits of that data that are not in the hub or the link, or the satellites that are appropriate for describing the link relationship or the hub itself. And one of the things that I've found repeatedly is, as I've done various database implementations, is anything that does not get organized with a data structure has got to be organized with application code. And I'll give you 3 guesses which one's more performant. It's not the application code. Okay, so here's just some more of the definitions of it. There it is. Some more of the definitions. So functors, groups to set, categories to groups. Basically, any mathematical object to any other mathematical object are transformed via this mechanism called functors. In our world, this is known as an ELT process. This is an ELT map. In mathematical terms, these are functors transforming subgroups into either sets or other subgroups. All right, let's take a little bit of a breath here. I'm trying to stay cognizant of time. So we have a process that we've kind of identified for starting to work with an application data model that we've never seen before and put it into a data vault structure. Analyze the application data model with graph theory, and then in 7 steps, you've got a good idea. It may not be 100%, as I said before, but you have a very good idea of what are the business keys, what are the relationships that are going to be important to the business, what are the traits and such. And we'll talk more about the traits in just a moment. And so I've been talking pretty heavily for a little bit. Are there any questions while we're on this slide before I go on to the next one? Okay. Now, as you know, we have satellites that are associated with a hub. How many what is the right number of satellites to be connected to a hub? How long is the string? Everybody has a slightly different answer. And one of the things that I hear repeatedly is storage is cheap. Well, storage is cheap, but depending on how the data is organized, that's going to affect your query performance, and that's where things are going to start to be expensive. Some of our cloud databases like Redshift and certainly Snowflake, they're great at performance. They're just phenomenal. I'm a big fan of Snowflake. However, if you design something poorly, no matter how fast the engine is, it's still not going to be efficient. So in order to identify the satellites, let's go back to first principles. What is the math that can be applied here? And so a little bit of puzzling that I did through is how many actual select queries can be put together without a group by, without a where condition or casting one column to 2 or more, just in general for any table. Well, the answer is the number of columns, so 2 raised to the number of columns for that table minus 1. The reason for the minus 1 is it could be a little complicated, but essentially you can't have a null select from a table. Just, it doesn't make any sense. And it doesn't answer this question because you're looking at the tables as they are defined in the relation definition. Now, if you have, let's say you have a single satellite with 40 columns. So that includes all the metadata columns that are appropriate for Data Vault. The number of queries that can be run against that table is 1.099 times 10 to the 12th. So that is, there's 1.099 or 1099 with 9 zeros behind it. That's a lot. There's a lot of queries that can be run. Are you going to run all those queries? No. But that's just with that one single table. But if you combine that with all the volumetric data, this table could be really important. So it could be queried a lot. Does that satellite really need to have 40 columns in it? And if you do, how deep is that column going to be? In other words, you're going to have a lot of duplicate data in the 40 columns, right? At least more than likely. Um, and because that data is duplicated, yes, it's taking up storage, but it's also using compute. And in the cloud way of looking at things, um, compute and storage are costed independently. They're you still have to pay for still have to pay for these things. Even if you're running on premise, you're still going to have to pay storage costs as you get new disks, upgrade your CPUs, etc. So if we take a look at this one satellite that has 40 columns and using that column entropy analysis that I showed before, where you do the rate of change of the columns versus rate of change of the rows, if you identify, let's say 3 columns or 3 clusters of rates of change, and those columns break down into, there are 20 columns that are similar, 15 columns that are similar in a different way, and then 5 other columns. Each of these have they're very similar rates of change. That reduces by a huge, well over an order of magnitude, the number of queries that are available to be run in the query space for these 3 tables instead of the 1 table. What does that mean? Chances are, if you have one really wide 40-column satellite table, it's going to be very long and it's going to take up a lot of space. It could be gigs, terabytes, what have you. If you break it apart into various rates of change with the 20 columns, 5 columns, and 15 columns, those individual tables are going to, the 3 individual tables I claim will be smaller cumulatively than the one satellite that has 40 columns. And as such, if you're querying, for example, a lot of your queries are actually coming from the 5-column satellite, there's all kinds of interesting performance tricks you can do with caching, with other things to reduce the cost associated with running queries against that satellite, just by applying a little bit of math and doing some decent design. Now, checking the time. Okay. Tuples. So I mentioned before that a tuple can be thought of as a function. So we look at a link table and we see that we've got we're tying together 2 hubs. We're going to call this hub X and hub Y. They're stored in the link relationship between the 2 hubs. So as we talked a little bit about the dimensional data model, and everybody thinks, well, you have to transform anything into a dimensional data model before you can do analysis on it. Maybe, maybe not. If we look at the rates of change of the relationship within the link table between hub X and hub Y, the rate of change of each of these, delta X and delta Y, that looks strangely familiar. If we wear a mathematician's hat, you've got this, which is, of course, a derivative. Now, as the links grow in size, where they're tying together multiple relationships between multiple hubs, ultimately you could get to where you could have some very interesting things with partial derivatives. And these partial derivatives are going to represent the rates of change in the relationship between these various hubs. This particular mathematical expression here, in the worlds of computational fluid dynamics and the very sophisticated math, you're going to see this partial X, partial T plus partial Y plus partial Z, etc. All of it is equal to 0. In a closed space, and we're using fluid dynamics mathematics, that is true. With our link tables, that we're representing things like orders and people and logins to the websites and on, that's not equal to 0 because it's not a closed space. It's an open space. And as such, this can be really interesting mathematics from the perspective of how your data moves within your organization. And trying to model this really sophisticated thing from a data science perspective as a dimensional data model is probably going to be a lot more complicated. By definition, though, this is the way a link works. So having your data scientists understand what a link is doing and how some of this stuff can be applied, um, they're going to have a different perspective on your data structures after they understand this. Now, another way of looking at links is, of course, a graph interpretation. You have hubs over here and then hubs over here, and you're relating these things together. This is I'll say this is my first mental model of what a link really was a relationship between two hubs. Um, so if you only have two hubs, this is called a bipartite graph. As you're representing more and more uh, hubs, more and more business keys within the links, so three-party links, four-party links, etc., then it'll be an n-partite graph, and you can do some really cool visualizations with things like that. Um, so just using a hub and an individual satellite, you can do some really interesting things with clustering analytics to be able to identify how these things are behaving. So you don't necessarily need to have a lot of other transformations in order to work with this. Just a hub along with interesting satellite data is perfectly fine to input into a k-means clustering algorithm. Uh, Speaking of data science, um, hopefully everybody, or maybe not everybody's heard of this, but what are the odds of the number one coming up in a roll of a fair die? It's 1/6. Well, what this translates to is you have um, what's called the expected results, which are going to be the values on the dice itself, and you know that only one of them is going to happen. So assuming you have a product hub, the odds of any given product being chosen at any given time is 1 over number of rows. And since the hub is a set, which by definition of a set is unique, you now have the expected probability of a given product showing up at any given time. Now, using some interesting things like where clauses and such to narrow down the domain of what you're looking at, um, that's going to change the number of rows in your denominator. So it's going to change the expected probability of certain products showing up based off of perhaps maybe even the demographics of a customer or time of day or any of those other kinds of things. But the point is, one of the things that I've heard a lot of people claim is that they have to transform data from data vault model into something else before they can do math on it. Well, no, that's not a hard requirement. Depending on what you're trying to do, there are ways to leverage things within the data vault structures and still apply some pretty interesting mathematics to it. And again, why is this important? I've heard repeatedly the claim 80% of a data scientist's time is in digging around to get data. Well, if you're building a data vault and you're investing the time and effort in your organization to put together an adequate data model, an enrichment data model, an enrichment platform for your users to use, you should, in theory, be making life easier on your data scientists. So the 80% number in a data vault environment should go down significantly, because if data scientists understand the data vault structures and how they can be applied and looked at from a mathematical perspective, it should make their job a lot easier. One of my favorite quotes: laws of nature are written in the language of mathematics. The symbols are triangles, circles, and other geometrical figures, without whose help it is impossible to comprehend a single word. All right. I know I'm getting close to time, so I'm going to just flip through this. This is some analysis that I did on performance of databases related to applications and such. You can see that this is there's some inverse relationships here, and I can talk about that another time. If anybody's curious about this, let me know. I'll be happy to talk to you about it. Now, the presentation layer, for a lot of tools, they're expecting data to be in a dimensional data model. The reason for this is that a dimensional data model is in reality a combinatorial approach to being able to answer questions. Combinatorics is a really cool mathematical area, but essentially it's all boils down to this. It's a way of measuring how you count things, figuring out different ways of counting things. Well, a dimension in a fact table, there are different ways of counting things. So dim customer is counting the sales per customer. Date, you're counting by customer and date, on and on. So a dimensional data model is really a combinatorial structure. So we talked about the base process. We had up to step 7. Now, the last couple things that I want to add to this, there's 3 more steps. You want to deploy things to a database using an automation tool. Expose those data structures that are used in Data Vault to your data scientists, and you want to iterate and focus on business value rather than low-level infrastructure details. Some of the things that we can do, yes, it's fun to get around and play with all of the queries and database settings and things of that nature, but you just have to be careful that the business understands the value that you're bringing to the table. Now, all of this stuff that I'm talking about, this is the math that you work with every day. Calculus, combinatorics, category theory, economics, graph and group theory, information theory, ontologies, probabilities, relational theory, set theory, and topology. You're working with this whether you realize it or not. The definition of a genius is taking the complex and making it simple. That's attributed to Einstein. Dan, Cindy, Kent, others, they've been teaching these principles for years. They're the true geniuses. They're the things that are making this much more complex. The only thing I've done is give a vocabulary to what is already being done. And with Data Vault, the mystery of how to organize data just becomes a puzzle. And puzzles are solvable. Mysteries are not always solvable. All I'm doing is naming the parts. This is stuff that you guys use all the time. And whatever we measure, even if you're looking at things from a new perspective, whatever is being measured, you can improve it. Now, one of the things that I've had a couple people ask me is to be able to explain the difference in terminology from a data scientist to a data architect. Well, really, all that a data scientist is going to be looking for is similarity, context, and relationships. In a lot of ways, data architects and data scientists are really talking about the same thing. And here is an illustration of that. They're all talking about chairs, but everybody has a slightly different perspective on what a chair is. A feature set is just a table that has a lot of columns, and a machine learning model is an object along with the code associated with it. That's a very high level definition in a nutshell, but it's attributes that are derived from the feature sets that are organized in a particular way, and that's going to be your data science, your machine learning model. So everybody's talking about the same thing. Everybody's talking about chairs, but you can see that from a data scientist perspective, whenever they think of a chair, that's the chair that they're thinking of. The data architect, obviously a little bit more business oriented, and then your application developers and users, they have totally different types of chairs that everyone thinks about them in. Now, this is, I'm going to have to read this because I want to be very clear about this. So there's been a number of times where I've tried to put together a data warehouse and leadership has said, oh, we don't have time to build a data warehouse. The whole connotation of the term data warehouse in some areas is negative because they think it's going to take forever and you're not going to be able to get anything done. But if you change the question slightly, and this is one of the things that I've done, and I've actually been able to see some success with this, which kind of surprised me. But if you say, can we build an enrichment platform to support data science efforts that transforms data using functors, supports probability analysis, set theory clustering, graph analysis, topological analysis, n-dimensional dynamic data representation, produces data products that can support combinatorial reporting by connecting to an ontological knowledge graph, where we can reduce the load in any front-end data analysis by applying economic supply and demand theory, all of a sudden management goes, hey, that's a great idea. What's a data warehouse? It's so for those of us that are in the know, all of these complicated terms, it's, you know, it's fancy gobbledygook for let me build a data warehouse the right way And this is the art. These are the artifacts that you're going to get out of building a data warehouse. This is what comes automatically just by putting a data warehouse together. All right, last slide. Just remember, you can be greater than average. Don't be intimidated by credentials, whether that be your executives, whether that be data scientists that use all these complicated terms and such. I love to get into the weeds with other data scientists and talk about some of the nuanced details of what they're doing. But at the end of the day, if there's 3 or 4 of us, and we're the only ones that understand each other, we're not really bringing any value to anybody other than patting ourselves on the back. So being able to kind of translate this from the low level details and talk to the business about, hey, these are how some of the things that I can do can help you solve problems, can help you determine where you need to make some improvements. That's going to be where the true value lies.